So this talk will be 45 minutes for each. Okay, let's move on to the first talk. The first speaker is Takeo Igarashi. I'm very happy to have him today. It's my pleasure, and also it's my honor. Takeo Igarashi is a professor of computer science department at the University of Tokyo, and his research is in the cross section of interface and computer graphics, and he is very influential in both communities. That is interaction and computer graphics. And he conducted amazing research, and he awarded a lot of awards, like including ACM SIGGRAPH Significant New Research Award, or ACM CHI Academy Award, and of course, AsiaGraphics 2020 Outstanding Technical Contribution Award. So yeah, I'm looking forward to his talk, and we can hear his research related to creative AI and with interaction. Okay, so please join welcoming Takeo Igarashi. So Takeo, please take it from here.
Okay, so would you stop your screen sharing, and then I will start my screen sharing. Okay. Yeah, hello. I hope you guys hear me. Yeah, so thank you for the introduction, and I will today talk about human in the loop creative AI. So I think we have 45 minutes. So I plan to talk roughly 35-40 minutes. So please ask questions, anything like clarification or future possibility and so on. So yeah, just briefly introducing myself. So I am working at University of Tokyo, and I have been working on user interface and computer graphics in general. So in the past, I have been working on like sketching interfaces or multi-touch interaction or some fabrication projects and so on. But recently, yeah, everyone goes to machine learning. So I try to learn something about machine learning and then trying to make some contribution. So yeah, I have to admit that I'm still new to machine learning and still learning. So yeah, I appreciate any feedback to our work. Okay, so human in the loop. So I will focus on creative AI aspect of our work today. So yeah, so many people now working on creative AI, right? Especially deep learning. So content generation by deep learning has lots of potential, and then many people try to develop novel techniques for generations. Artificial intelligence, mainly neural network, do something and then get many kinds of media contents like images or 3D models or animations and music. Yeah, anything. Yeah, so many people are doing it. So our group specifically focusing on human in the loop aspect of it, not just let AI to do whatever and then just get the result. We try to bring human into the loop. So typical interaction is to AI do something and then user sees the result, and then user do something to modify, give feedback to AI, and AI produces the next round. So this kind of iteration, then gradually a user will get what he or she really wants. So that's the overall scenario. Okay, so so our group working on in this direction, and within this framework, we published a couple of papers. So I want to introduce some of these papers projects. So the first one is not really using deep learning, but I think this is a basis for following papers. So I want to introduce this work first. So this is mainly a project by Yuki Koyama, who got PhD from our group. So this one is titled Sequential Line Search for Efficient Visual Design Optimization by Crowds. So let me first show you the teaser video. I hope it plays. Oh, wait. So yeah, there's no audio. So yeah, let me go back. This is too fast. Okay, so I hope you see video, right, Nobuyuki?
Yes.
Yeah, so target problem is parameter tweaking. For example, if you want to adjust photograph, you have to control many parameters, which is difficult. So that's a problem. So here in this project, we plan to ask crowd workers to work on this together. You know, individual people do micro tasks and we aggregate. So that's the idea. So each crowd worker do very simple one slider task and then we aggregate it. Right? So but once each crowd worker manipulates only one slider, but is associated with high dimensional or space exploration. And then after get the result, then we move on to the next round, next round. So in this way, we accumulate feedback from crowd workers, micro task result, and then eventually we get a good result. So internally, the system maintains a like optimization space and then tries to get the optimal in the parameter space. That's what's going on. So this is applicable to photo enhancement, to a material design, and so on. So this is just a teaser. Okay, so let's explain step by step. So the target program here is parameter tweaking. So there are many applications for parameter tweaking, like image enhancement, like Photoshop color change, or material design in Blender, Maya, and so on. So you have many parameters like glossiness or specularity or color and so on. Yeah, there are so many other things like facial expression control with many sliders and viewing angle control. Yeah, parameter tweaking is everywhere in computer graphics. So that's a problem we wanted to address. And this is very difficult, right? So expert can understand the meaning of each parameter and then may be able to control appropriately. However, for novice users, they have no idea what each slider means, so they have to test. And then, but one slider and then get the optimum result, but move on to the next slider, then, you know, the relationship between previous slider is also complicated. So this is very difficult exploration task. So we want to help this with computers. So our approach is to divide this complex high-dimensional search program into a micro tasks. So in this particular publication, we focused on crowdsourcing because it was easier to run user study. But I think the basic idea can be applicable for single user operation. You know, single user to sequence multiple micro tasks and then get the result. So anyway, the essential part is divide big problem into small programs. Okay. And then in this particular paper, our contribution was new MicroTask design and then algorithm framework. So for MicroTask, we proposed a new way of interaction called sequential line search. And then for algorithm framework, we proposed a Bayesian optimization method. So yeah, MicroTask. So typical approach to get MicroTask feedback from crowd worker or single user is pairwise comparison. So this is very classic and very popular. So the system shows 2 or 3 or 4 couple of choices and then asks you that which one is better. And then system updates internal state representation and then asks the next question and then repeat it. So this is very easy to understand, easy to implement and very popular. Everyone uses it. However, the problem is that information the computer can obtain from the user feedback is very limited. You know, 1 bit information from one user task, which is very limited. So then end up the search time is very long, right? Each step, the information is limited. So the system have to ask many questions. So our idea is replace radio button with a slider. The user explores this continuous one-dimensional subspace and then pick the best one and then press next. And then next one-dimensional subspace is presented and the user searches in the subspace and then pick one. So system, the user micro task is to pick the best parameter value, best position in this one-dimensional slider space. So this is much rich information, right? So this one point is better than many other points in this one-dimensional space. So system can obtain rich information, then the faster convergence. So that's the idea. And as for the algorithm, we take a Bayesian optimization approach. So Bayesian optimization is a machine learning technique to get as much as information from minimum input from the Oracle. So yeah, this is just a explanation. So I think this dot line is ground truth. And then these dots, these circles are the feedback from the user, right? So the system shows a query and the user feedback there. And the system shows a query and user feedback there. The system asks this question and user feedback. And then this red one is the estimation of the computer. And then the most important part is the system asks the next question. So so next question is a main problem. And then system asks the right questions to get maximum information gain. So there's a technique. So suppose this is a two-dimensional parameter space, and the user is explore this one-dimensional subspace and they pick the best one. And then system updates the representation and then next one-dimensional subspace and user pick one and then repeat this. And we ran a simple user study and the result is very good. So we compared against like two-way comparison or four-way comparison. And horizontal axis is iteration and vertical axis is error. And our method was much faster than two choice or four choice and so on. So sorry, let me skip the others. Okay, so next one is that we apply the same idea to generative image modeling on using deep learning. So yeah, interactive optimization of generative image modeling using sequential subspace search and content-based guidance. And this one is a project by so this also is wrong, I think. Sorry, I have to fix this later. Yeah, so so basically it is simple. We apply the preferential Bayesian optimization to generative image modeling, right? The idea is the same. We have a parameter space, and then we pick the set of parameters values, latent vector values to the network, and the system shows the result. And then a user sees the result and then provide feedback, like one slider, and then update the parameters, and then repeat this. The benefit of using this approach is the pluggability, right? So system can just use a neural network as a black box. So no need to get internal information. User just sees the result, give feedback and change parameter, and see the result and change parameters. So we can apply the same idea, same architecture to many applications like noise to image synthesis or image to image translation or text to image translation. Whenever the system gets some latent variable, we can change the latent variable, latent vector, and then control the result. So that's the idea. So the problem is that, original parameter search problem was low dimensional, like 5, 6, 10, something like that. But here, I think this dimension is very high. I think this one case was 512. Yeah, sorry, I don't exactly remember. 512 dimension or 512 by 512 dimension. But anyway, very high dimensional. So which is very difficult to reach optimum using Bayesian optimization. So in this particular publication, we propose two methods. One is to use multiple sliders, right? Instead of one dimension, one slider, it takes time. So we present 4 sliders and then ask user to control the 4 sliders in each step. The other extension is to let user to paint the image to guide the optimization process. So multiple slider looks like this. If the search space is 2-dimensional, the system shows 4 points in this subspace, like 4 images, and then user control the weights to these candidates. And then this is essentially running a search in this small region surrounded by these 4 points. And then in the next iteration, next subspace is presented, and then we repeat this many times. And content-aware sampling, like this painting one, works like this. So yeah, this is a little bit complicated, but Bayesian optimization tries to find the point that maximizes acquisition functions. And the acquisition function is basically this expected improvement, right? So expected improvement means the data point where the system can expect the best increase in the value, right? And then we add content-aware term to, how to say, bias this acquisition function towards as what user expected. And we add some regularization term. And then content-aware term. So this term looks like this. It's basically just add through the pixels and then compare the reference image painted by the user and then current image and then compute the difference. So let me show you the video. The video running. Yeah. So yeah, so there are 4 images and 4 sliders, so which means the weights, and then control the weights to get the most desired image. Yeah, this is painting control. So by repeating, then you get to the desired result. Okay, so we applied this idea to various applications. So first one is noise to image. So we apply this to PG gun. So get the latent vector and then get the control, and then we get this kind of result, you know, the initial result and final result. Initial result and smiley mouth, and then get the final result. Next one is image translation example. So this is a user input, and then this is initial result. And then user paint in red, and then the system finally results looks like this. This is another example, like line drawing or bag, colored bag, user paint, and then final result. And one more, text image. So user input is a red bird with yellow belly, and you get this result. But this big mouse is too small. So user paint, and then you get this result. Or this is another example, black wing with white belly. But this belly is too small. So use a paint this way, and then you get this result. So that's the interactive optimization of generative image modeling using sequential substrate search. Okay, so next one. The next one is essentially trying to solve the exactly same problem, right? You got a latent variable, network, and you get the result. And the user feedback, and then do the same thing again. But in this particular paper, novel contribution is take differentiation gradient from the neural network, right? So the previous paper, we completely use this generative model as a black box. We don't use any information from this structure. However, you know, neural network is differentiable, right? So that's a very strong benefit. So by taking that differential, we can use this information to accelerate the search. So that's a basic idea. And I think it's better to show the video first. So user interface is basically the same, right? So let me skip. So yeah, user interface is the same. You know, user control the slider and press next. And then user control the slider and press next. So that's the same. But the contribution in this paper is to the picking selection of this subspace, which subspace to use. So that's the question. And we apply the idea to many applications like image synthesis in the MNIST space. And also we apply the same idea to 3D model generation. Yeah, the very same idea of latent vector generates a 3D model. So we just explore the space, latent space, by providing feedback in this one-dimensional slider. And I'm not making sound here, but you can apply the same idea to sound design if it is a latent vector-based generative model. We just control the latent space and you continuously hear the sound, synthesize the sound, and give feedback. And eventually you get the desired sound. So that's the idea. Okay. So yeah, let's just same thing. So user interface is the same, one slider, image generation, sound generation, and 3D model generation. So we only need just a gradient of the network. So algorithm looks like this. Yeah, let me go a little bit of detail. So it works like this. So latent vector is Z, and then you get a neural network function, and then you get X is output of FZ is X. And after getting X, user see the output X and then evaluate it. And then finally, evaluation result looks like this, right? Latent vector is Z, and then neural network is F, and then human perception is G. And then the problem we want to solve this optimization problem, right? So we want to maximize Z while changing Z. So this is a problem we want to solve. The problem is that G is, this is black box. We don't know anything. However, we know this one. This is, in a sense, white box. We can differentiate it. So that's the idea. So this is what we want to do. We want to optimize this function, and then we use basic gradient descent. So we want to take a gradient. So then gradient looks like this, right? So we take derivative gradient of this function. And then if you look carefully into it, then we can separate F gradient of differential of F and G part. And then G part is unknown. So we have to ask user to provide feedback. But this F part, we can actually compute. So in this way, you do some calculation, and then, so in the end, you will get a much simpler result. So this part is system computation. So taking the gradient. Now this one is a user feedback. So in this way, you can get much efficient search. So yeah, this explanation is a little bit complicated, but in the end, it's very simple. So in the high dimensional space, you can many possible directions to go, right? So some direction, you see lots of change, but in some direction, you don't see much change. And in order to do search efficiently, you should go to the direction with lots of change. And it's very meaningless to control slider if there is no change. So this example shows that situation, So yeah, first eigenvector, which is more direction with biggest change. You can see clear change here. And then 24, a little bit of change, and 256, there's no change at all. So the idea is simple. So we just try to find the direction with maximum change. So that's the idea. And the result looks like this. This is very efficient, right? So Bayesian optimization, which I described before, doesn't work well for high dimension. So if you use only one slider, it doesn't work well. And random presentation is random selection of the direction is slightly better, but proposed differential method is much better. So yeah, that's this work. Okay, so next one. Next one is a different topic, and this one actually not really human in the loop, but let me show you an example of project we are working on in generative modeling, image modeling. So the problem here is texturing of line drawings. So these black and white line drawings are the input. And then target task here is to put texture like this one. So standard approach, naive approach is just flat pasting of flat texture, but looks too flat. So we want to get some impression of three-dimensional shape. So that's a problem we wanted to address. So one traditional approach is just inflate the closed region like a balloon, but it doesn't look right for this kind of garment, right? Garment surface should be developable. So we should use some knowledge about the development, garment thing. So the idea maybe straightforward today. So the idea is basic. So we just use machine learning approach. So we create 3D model of garment and then run simple driving simulation and then take many training data. It's basically a pair of three-dimensional data and then 2D ink rendering. Then we train a network for taking the line drawing and then returns texture mapping. So the core idea, main contribution of this work is in the training, we use three-dimensional information, but in the neural network, we only use the input as two-dimensional image and the output is local distortion in the mapping from image space to the texture space. So we skip three-dimensional representation and we directly compute the mapping from image to texture space, image space to texture space. And we also infer local deformation like stretch or squash and rotation. So we just compute local transformation in the neural network. So this is the output of neural network, and it's lots of local transformations. And then we integrate, stitch together these local results, and then you will get the UV mapping. So that's the idea. And this is a result. The approach. So direct. So this is our result. So we see natural, therefore reasonable result like sleeve is bending. And then we also tested, neural network returns normal map, and then we do flattening to get the result. And also we also experimented with directly computing normal map from deep network. But however, in this case, it's very difficult to represent this curve of bending of the texture. And our main target here is texture mapping for like black and white comics or illustrations, right? So traditional approach is just two-dimensional flat screen tone, but with our approach, we can get some reasonable three-dimensional deformation. Okay, so lastly, we want to show a couple of projects on music and audio. So first thing, one is a kind of naive application of the Bayesian optimization approach to melody synthesis. So the idea is the same, right? So the system generates multiple melodies, and then user selects one of them and then give feedback. So by repeating this, then you will get a desired melody. So I think audio is important. So let me stop screen sharing first. And then let me screen share again with audio sharing. Okay. Yeah, sorry, I'm preparing video. Yeah. So
we proposed a mechanism to generate melody composition with human-in-the-loop Bayesian optimization. We implemented and verified our idea through a web application. This system facilitates the explore. Those candidates can edit the select until the user is set 15th note duration. Each row represents a key on the piano from C3 to check whether they are satisfied with them.
The user edits a melody and then
button. Delete them by clicking. Choose two bars and open the searching interface. In the first iteration, candidates are randomly and uniformly sampled on the dimension-reduced latent space of the pre-trained generating model. The two bars the user selected are shown in the editing region. We suppose the user prefer the melody in the editing region to the candidates.
Sorry, it's too slow. Okay, yeah, let me skip this one. So, okay, so the idea is the same, right? The latent space, melody synthesis, user interface, user internet page optimization. So we did this first. And then, so next here, we extended this, we add new feature in the next version. So in this new version, which I represented intelligent user interfaces, was to let user to balance between exploitation and exploration. So exploitation means you already have a reasonable result, and we just search near the current best result, and then tries to get the best possible near the current best one. But exploration is current result is not so good. So user think something better may be far away from the current best optimum. So we want to go far away from the current one. So in a sense, exploration is a long range search or global search. And the exploitation is a very local search, narrow range search. So in this new version, we allow the user to specify which way to go, like narrow local search or wide global search. And then this additional control gives more control for the user. So yeah, so we tested this interface and we found that user really like this. So yeah, motivation was that without this one, in the previous interface, a user wanted to that kind of control, user dislike just blindly choose a candidate. They really want more control, sense of control. So we found that this kind of mechanism is very helpful to let user to give further feedback to the system. Okay, so final one. So final one is fully perceptual based 3D spatial sound individualization with an adaptive variational autoencoder. So it's complicated, but basic idea is simple, just the optimization of 3D spatial sound. So 3D spatial sound is, you have a head-mount display, virtual world, and then stereo sound, and then system tries to give sense of 3D sound. So not just left or right, system tries to give illusion of the sound coming from front to above or behind and so on. So that's what we want to do, 3D spatial sound. So in order to do 3D spatial sound, we have to modulate the incoming sound, right? Source sound is modulated in some function, which is in reality, modulation happens because of the user's particular shape of head and ear and the inside structure, right? So yeah, so source sound is modulated when it reaches to the inside of the ear. And then this modulation is different from left and right. And from the difference, the people will perceive the direction. But the problem is that this transfer function is highly dependent on the individuality of each person. So each person has different function. And in order to achieve this 3D audio, we have to, replicate this function, but it's very highly individual. So traditional approach is to measure this function physically using this special chamber, special loop, right? So put the microphone inside of the ear and they produce sound signal from various directions and records the relationship between source sound and then microphone gain. However, obviously, this is unrealistic to use this technique for each user, right? Each user have to go there, take measurement, and then just benefit single user, so which is not ideal. So approach is to leverage data-driven approach and also, human in the loop optimization. So that's the idea. So first, we collected So there is a public data set of this measurement of 45 persons. We have complete set of this filter data. So we train a generic model from this publicly available data set. And then we do some structure analysis to separate this one with individual part and then non-individual factor. So this is the training part, pre-training before inviting specific target user. And then new user comes in, and then we want to calibrate or customize this generic filter to this target user. So in order to this optimization, we do the Bayesian optimization kind of thing. This is again parameter space search. The system provides some 3D sound to the user, and the user gives feedback. This is better. This is worse. This is better. This is worse. So repeat this process many times, and then system explores the parameter space, and then eventually user gets the best 3D sound filter. So that's the idea. So this is a kind of interface for user feedback. So system produces sound from this direction, like left. Yeah, this indicates 3D position, and then produce sound from here. And if the user think the sounds like coming from this direction, and then says good or not. So in this case, we show two possibilities, A and B, and ask the user which is better, like comparison feedback. So it's very difficult to demonstrate the strengths of technique. So we just show one snapshot from user study. So we provided 3D spatial sound to the user, and they ask the user to point the incoming direction of the sound. And this one shows that this is a ground truth, and the user answer is very accurate. Okay, so that's it. So so because of this limited time, we focused on the human in the loop generative modeling. And we first introduced parameter search, and then we showed application to image modeling and audio modeling. Thank you.
Thank you very much for inspiring talk. So we can take a couple of questions. Please, if you have question, please post it on the chat. While everybody posting a question, let me ask the first question. So in the loop optimization, machine learning, so the user will input the latency space vector directly. So I think it's a little bit rare that user inputs the latency space, directly inputs the latency space vector. For example, in many machine learning model, people will input the image and hope to the image is translated to another image, or something else. We may want to input the sketch or sound or text. Is it difficult to construct human in the loop kind of machine learning other than directly editing the parameter space?
I think that's what other people doing, right? So they usually latent space is not exposed to the user. So I think typical approach to try another network that take user input and then applies update. And so that's a typical approach. So as a research, we want to do something different, and we want to try what happens if we allow the user to directly control a latent vector. And obviously, this may not be the best interface in some cases, but in some cases, it's very difficult to give direct control. For example, music may be difficult to give feedback, or strange sound. It's very difficult to distinguish, explicitly specify which way to go. Then in this kind of latent space exploration may be useful. So we do not claim this is the best possible good but this is still experimental, I would say.
I see. So what is the use case for finding such a kind of latent vector? So is that some, like a situation that user want to find out the latent space vector?
Well, the example I show is basically, I think, small adjustment to the result.
I see.
Neural network result may be not perfectly satisfactory, and then we want to check what's possible around this one. This kind of user may want to know what's possible around this particular result. So in this case, this kind of interaction may be helpful rather than just let the computer to do everything.
I see. Thank you. Yeah, please post the question in the chat. So maybe I'll ask another question. One other question this time around. So I was surprised, a bit surprised that one-dimensional search, when we combine them nicely, we can find out some optima. Because I expect that the parameter space, the user's preference, like G bracket F bracket, would be more jaggy, a lot of local minima, and it's and I was a bit surprised that one-dimensional search performed such nicely for many applications. Do you think this is this is because the human preference is kind of smooth and does not so affected
that's
by?
Interesting question. Yeah, first I want to clarify that this work is definitely just a local search, right? This one just goes to the local minimum or local maximum. So this doesn't guarantee global maximum or so that's one thing we want to clarify. So user just goes to the local one. However, my guess, there's no proof, but my guess is that generative model can do amazing things, but still very limited. You cannot do whatever. You can just basically mixture of training data, in my understanding, in exaggeration. So what you can get from this generative model is kind of limited. So then in these limited variations, user preference is, if user wants to do some target, then it's just a kind of, smooth field. One desired one is the best one, and the others are gradually, getting far away from the result. So that's my guess.
The manifold is smooth.
Yeah, in this particular tasks.
Thank you very much.
There's one question. It's almost there's a question. Go ahead.
So there's one question from Ruizhen. For 3D shape modeling, it is possible to let the user as a control directly to the 3D shape instead of latent space. Then map the user control to the latent space to the Geyser modeling. It should be more intuitive.
Yes, I agree. That's something we want to do next. So it's today presentation is complicated. So the first one presented used Bayesian optimization one, right? So if we apply this content-based guidance, Bayesian optimization, it's possible to control already if you apply this idea to 3D. But however, in the new one, differential subspace one, improved one, currently do not take any content-based control. So that's something we want to do. And I think it's possible, right? So the core part of this work is to find a good direction to go. So currently, when looking for direction, we just look for biggest variation, biggest change direction. But we can tweak the direction selection when the maximum change to the desired change or minimum change to the fixed part, something like that. So that's something we want to do next. Thank you for the question. Okay, I think that's time, right?
Yes. Yeah.
So just advertisement. Yeah, so we are looking for interns or visitors, everyone. So if you want to come to Tokyo, please apply. Thank you.
Yeah, thank you very much
So
for
let
excellent
me
talk.
stop my. Thank you.
Thank you very much. Okay, we move on to the next speaker. Yeah, I'm also, it's my great pleasure to have Ruizhen Fu in this session. Ruizhen Fu is an associate professor at Shenzhen University, China. She received her PhD from the Department of Mathematics, Zhejiang University. So before that, she spent 2 years in Simon Fraser University, Canada, and her interest is computer graphics and machine learning, and she received the AsiaGraphics Young Researcher Award in 2019. She also served as a program co-chair for SMI 2020 and is the editorial board for the visual computer and CG and application. Okay, then please start your talk.
Okay, thank you for the introduction. Can you see my screen?
Not yet.
Oh, yeah. I already shared the screen.
It's starting. Yes.
Okay, great. Okay. So thank you for the introduction. Hello, everyone. This is Ruizhen Hu from Shenzhen University. Today, I'm going to introduce several works that use reinforcement learning to guide shape manipulation, especially in the case of using robotic arms. And let's first take a look at this video. Here's a robotic arm need to grasp the object on the table and place it on the box on the left. And this work focused more on the grasping itself and didn't try to optimize the placement of the objects in the target box. And the initial states of the objects are upright oriented, which makes them easier to grasp. And the two works I'm going to introduce today can be considered to have a similar goal, but with optimization focused on different stages of the task. And the first variation is what we call as a transport and pack problem, where we simplify the objects and grippers and focus more on the packing order and final packing state. Given an initial configuration of objects, the goal is to iteratively transport and pack the boxes compactly into a target container. And the second variation is what we call as a grasp and place problem, where we don't consider the packing of the objects, but instead focus more on the grasping and placing task, which requires the robotic arm not only to grasp the object successfully, but also to place the object stably on the table in its upright orientation. One common property shared by those two problems is that although they both have very clear and quantifiable goals, there might be multiple optimal solutions for the same input. That is, the optimal solution is not unique. For example, for the first step problem, the input boxes can be packed in different ways into target container, but with the same final packing effect, as we show here in 2D for clear illustration. And while for the second gap problem, we can see that the final state of the object still has 1 degree of freedom and can be rotated around the upright direction. When solving those two problems, we found that for this type of problem, using reinforcement learning to find a policy to guide a path to any optimal solution can get better results than using supervised learning method that tries to directly map to one optimal solution. So next, I will give more details of how to use reinforcement learning to solve those two problems. And for the first tab problem, I just mentioned that the final goal is very clear. That is to find a good packing for a set of given objects. So we first define a metric to evaluate the final packing quality, consisting of compactness, pyramidality, and stability, which I think are quite intuitive and standard for packing problems. However, unlike previous packing problems studied in computer graphics, which usually assumes that a set of shapes are given without interconstraints and focus on the packing problem itself. Well, in some other real-world applications, the objects are already in a physical arrangement, and the object movement must follow a partial order with access constraints. Here we use a robotic gripper to help illustrate the access constraints. In each step, we need to pick one object from the input set and then pack it into the target container. As shown in this example, object E can be successfully transported, while object A cannot, since object D blocks its way and needs to be moved first. To adjust this problem, we first encode the access constraints into a precedence graph. In more details, we allow the objects to be rotated during the transport and the packing process. So in 2D, each box will have two different states, the original state and the rotated state. And the precedence graph is used to indicate whether each of those two states is valid given current object arrangement. To construct the graph, we extract three types of edges to encode the precedence relation due to the blocking from the top or the side, including TB, LAB, and RAB edges. TB edge indicates top blocking. For example, box E blocks the top of D, so there is a TB edge pointing from E to D. LAB edge or RAB edge means the access to the left or the right side of the box is blocked for rotation. For example, box E blocks the access to the left side of B, and C blocks the right side. And here is the complete precedence graph for the input set given on the left. To pass the information stored in the precedence graph to our network for packing optimization, we need to find a way to encode all those nodes and edges. So for each box, the original and rotated state are encoded respectively. And we encode each state using its size and encode the precedence information using binary codes. For example, box A is pointed by two TB edges from E and D. So both states of A, the corresponding positions in TB encoding are set as 1. For the original state, the LAB and RAB are all set as 0, since it is only used for the rotated state, whereas the corresponding position in LAB and RAB encoding are set as 1. Therefore, the only condition for packing any state of any box is that its precedence encoding are all 0, like box B in this case. Note that the geometry information of the shape is static during the whole process, but the precedence information is dynamic, which will be updated when an object is selected and removed. For example, when box E is transported and packed, edges related will be removed and the corresponding code will be updated. Now we have the information encoded in the precedence graph and with a target container, our Tabnet starts to find objects for packing. In more details, Tabnet consists of an encoder, a decoder, and an attention module. The encoder encodes both the static and the dynamic information from the precedence graph. The decoder is a recurrent neural network. For each time step, it takes the object selected in the previous step and the current height map of the target container as input, and pass the accumulated information to the attention module with the encoder to compute the probability of each item valid for transport and packing. And the item with maximal probability is selected to be the output. In this example, box E in its original state is selected. The removal of box E will introduce an update of precedence graph, and packing E into the target container will lead to the update of the packing height map. So all the dynamic information gets updated. Moreover, the item coming from the same object, that's box E in the rotated state, needs to be set as invalid as well. With the information back to Tabnet, the next object will be selected, which is the rotated box B in this case. The whole process iterates until all the boxes are transported and packed into the target container. Note that our Tabnet only outputs the packing sequence. To find the packing position for the selected boxes, we employ a simple heuristic strategy, which tries the bottom left corner of each empty maximal space and selects one with the highest packing quality. We actually tried more sophisticated learning-based packing strategies and find that this simple packing strategy works best with our Tabnet. Our hypothesis is that the heuristic packing placement strategy are more predictable, and hence it is easier for Tabnet to anticipate where the next box will be placed and output the optimal box and its orientation accordingly. And to test our method, we designed two datasets. The first one is random dataset. The initial box configuration was generated randomly. And the second one is called the perfect packing solution guaranteed set. To generate the initial configuration, we first generate a perfect packed target container, what we call as Candidate Perfect Packing Solution, CPPS. Then we take the boxes out of the target container in sequence to form an initial configuration, which guarantees to be reversible for packing back into the CPPS, which means for this set, we know that the perfect packing result exists. Here we show some tap results in 2D on random dataset and a PPSG dataset. We can see that Tabnet is able to find perfect packing solutions other than CPPS that are used to generate the input testing data. Note that our method can easily be extended to 3D where the whole process is the same, and we just have 6 different states for 3D shapes instead of 2 in 2D. And while for the packing quality measure in 3D case, an object is considered as stable if the projection of its center is inside the region formed by the supporting points. Here are some results on 3D cases. Each case is shown with the front view and the back view of the container. Then for the second grasp and place task, we focus more on the problem of upright orientation estimation, which is a typical geometric analysis problem. There are some early works that were built based on handcrafted features, which makes them work in limited conditions and require high quality 3D shape as input. Recently, a DNN-based method has also been developed, but the network needs to be trained separately for different object categories, and the input shape is represented using voxels, which is time-consuming and storage intensive. So to solve those problems, our goal is to design a more versatile neural network, which can estimate the upright direction of the input shape, no matter it is represented by a complete or partial point cloud or even a single scan. And the key idea of our method is to consider it as a sequential decision-making process where we train an agent to rotate the input shape step by step until it is upright oriented. Here, the initial and updated states of the input object can be considered as observation, and the action is sampled from a set of predefined rotations. In more details, if we assume that the positive direction of the z-axis, shown in blue here, is the desired upright direction, then we can add 4 rotations into the action space, including rotation around the x-axis counterclockwise or clockwise, and a rotation around the y-axis counterclockwise or clockwise. And then we can define an extra stop action that allows the agent to terminate the iteration by itself. With this action space, we can design a network to select a sequence of action to perform upright correction for a given shape. Here is the network structure of our model called upright RL. In each iteration, we extract the point cloud feature using PointNet. Then the agent will output the probability of those 5 actions. And one action is sampled and applied to the input point cloud to get the updated state. The updated point cloud will be the input of the next step, and the iteration will stop if the stop action is sampled or the maximum number of steps is reached. Then to guide the training of such a network, we need to define a reward function to evaluate the action applied in each step. So we compare the 2 point clouds before and after applying the sample action. Here we use the orange arrow to represent the current upright direction of the point cloud, and the blue arrow to represent the target upright direction when the shape is upright oriented. So intuitively, we defined a reward function to encourage the orange arrow to get closer to the blue one with smaller number of steps. And we consider the upright correction to be successful if the angle between those 2 directions is smaller than a given threshold, as in previous works. But instead of setting the threshold to be 15 degrees only, we also tested 5 and 10 degrees to evaluate the result in a more accurate manner. Then for a testing set, the success rate is used as the evaluation metric. And to collect those different type of input data for testing, we built 3 data sets from the completion 3D benchmark. And note that since we know the current upright direction of each point cloud during training, we also designed a network called BaseNet to predict such direction and using supervised learning. This table shows a comparison between our upright and the BaseNet on those 3 datasets. We can see that our method generally produce more accurate results than BaseNet. The difference is more clear, especially when setting smaller threshold. For example, the success rate on the 5 degree of upright RL is more than 2 times higher than that of BaseNet for all 3 datasets. Here are some view comparison between our model and BaseNet. We can see that even for partial input with large missing part, our method can still successfully rotate it into its upright orientation. Now, with upright direction obtained by our method, let's get back to the grasp and place task. Given an input lying on the table, we first take a scan to get the input point cloud. Then we use the GraspNet to get a set of candidate grasping poles and our model to get the upright direction. Here we use a gripper skeleton to represent the gripper and the orange arrow to represent the current upright direction. And our goal is to select an optimal pose to grasp and place object in its upright orientation. So we propose a grasping pose selection method based on the upright direction. The first step is projection filter, where we project the input scan and the gripper key points onto the upright direction. If some part of the gripper projection lies outside the scan projection, the gripper will collide with the table while placing the object. So we consider this kind of pose invalid. And this is a valid pose whose projection is fully inside the scan projection. These are all the valid poses left after the first projection filter step. And the second step is angle selection. We think that when the grasping pose is perpendicular to the upright direction, the contacting region will be larger and the final placement will be more stable. So we compute the angle between the grasping pose direction and the upright direction and select the one with the angle closest to 90 degrees. And with this optimal grasping pose we selected and the upright direction, now we can control the robot to grasp and place the object. Here are more demo of grasping and placing different objects. So by now, I briefly introduced the 2 works on shape manipulation using robotic arms and how they can be solved via reinforcement learning. Actually, similar methods can be used to solve problems in other areas. And I will give one more example in data visualization, which may seem irrelevant at first, but eventually it is also about shape manipulation in a sense. Star glyphs are a type of radial plot that show data points in a compact representation with the coordinate axis circularly arranged around a central point. And the order of the coordinate axis heavily influence its shape and thus its perception during analysis tasks. The desired shape of a star glyph depends on the visualization task. Most existing works study the coordinate ordering problem for a single star glyph with the goal to improve properties like symmetry or saliency. But for similarity search and grouping among a set of stack glyphs, especially when associated to multiple class labels, the perceptual difference between glyphs becomes more important. So in this work, our goal is to maximize visual class separation by optimizing the coordinate order of the glyphs. That is, to minimize the interclass shape distances and maximize the interclass distances. So essentially, it can be considered as a reshaping problem by reordering the coordinates. And to solve this problem, we propose a reinforcement learning-based method for coordinate reordering. The network architecture is actually very similar to the one we used in the transport and pack problem, since both problems aim to find a good sequence order for a given set. So the key in this problem becomes to define a proper reward function to guide the training of this ordering network. As I mentioned, the goal is to maximize the visual class separation. So we define a shape-driven class separation measure as the reward. And the first keyword is shape-driven, which means we want to define a perceptual distance measure between two stack glyphs based on their shapes. And a natural choice is the classical shape context descriptor. In more details, given a stack glyph represented by a 2D polygon with first sample points on its boundary. And then for each sampled point, we create a grid and compute the relative position of the other point by counting the numbers of points falling in each bin of the grid. Then for each sampled point, we can, after the counting, we can create a spatial histogram, which is the shape context descriptor of the central point, and it can be stored as a two-dimensional matrix. To measure the distance between two shape context descriptors of 2 points, we employ chi-square test between the two histograms. And for two stack glyphs, their perceptual distance is defined as the average distance of all pairs of shape context descriptors of the corresponding points. Note that the sampled points are naturally in correspondence along the boundary, following the coordinate order. With the shape distance of each pair of stack glyphs, we measure the class separation of the entire set by silhouette coefficient, which is also a very common measurement in clustering problem. It first measures how similar a shape is to its own cluster compared to other clusters, and then takes the maximal value over all cluster means as the final silhouette coefficient. And high silhouette coefficient indicate better class separations. We conduct a user study to justify our class separation measure. In this study, users are shown with a set of stack glyphs without labeling. Then they are asked to manually group the glyphs into clusters. Note that the size of each cluster can be different, and the number of clusters is also decided by the users. So the average grouping quality The result will indicate the perceptual class separation of the stacked leaf sets. For the study, we randomly synthesized 10 datasets with various dimensions, class numbers, and sizes. For each set, we find coordinate ordering with low silhouette coefficient and a high silhouette coefficient. SC here is short for silhouette coefficient. And in addition, we add one more ordering following another strategy to present salient shapes with spikes for comparison. And here is the result from 20 users for those three orderings. The grouping quality is measured by comparing the user groupings and the ground truth groupings of those data. We can see that the ordering with high SC help user achieve higher grouping quality, which means that the class separation measure we proposed is useful and stable. In most situations, users were able to tell the perceptual difference between different glyphs more clearly for set ordered with a high SC. Here are some view results. We can see that the glyphs with optimized coordinate orders have better contrast between classes. And actually, the proposed method can also be generalized to other types of plots, like radar width, which arrange each dimension around a circle and plot high dimensional points inside the circle. Different coordinate ordering can also lead to different perceptions for radar width. And just like stack glyphs, we also want to optimize the coordinate order for radar width for better separation between classes. So we can reuse our network, but with the reward function replaced by the class separation measure commonly used for radar width. And here are some view examples. We can see that the clusters are distributed further away in the optimized coordinate order than before. So to conclude, today I introduced two shape manipulation tasks and show how they can be solved using reinforcement learning. And then I show that the proposed method can also be used to optimize the coordinate order for a set of stacked leaves with a shape-driven class separation measure utilizing shape context descriptors and the silhouette coefficients. And I believe that the key is to formulate the problem in the right way. That is the way to encode the observation, the way to construct the action space, and the way to design the reward function. Due to the time limit, there are many technical details I haven't explained in depth, and limitations and directions for future works that I haven't discussed. But other papers can be found at my homepage. Please feel free to contact me if you find any of those work interesting and would like to discuss more. I'm ready to take any questions. Thank you.
Thank you very much, Ruizhen Fu. It was a wonderful talk. So yeah, there is about 10 minutes for Q&A session. So if you have question, please post it on the chat. Let me start one. So in your all research presented today, the network is based on sequence and using the attention network.
Yeah.
So why? What's the reason you choose this kind of architecture, especially for shape manipulation? Do you think it's such architecture have a lot of advantage over the, like simple encoder-decoder network?
Yeah, it's very good question. Actually, when we try to formulate the problem, it's a combinatorial problem, and it's even an anti-hard problem to solve. And we didn't find a very good solver. And then we start to explore previous works, like to see if there is any learning-based method can be used to solve that kind of problem. And we found one paper that was published on I think it's NIPS 2018, which is the setting is very similar to our problem, and the reinforcement learning network. The network architecture is very similar to the one I presented here, used to solve that kind of problem. And the main advantage of this of using this kind of network architecture is that it can efficiently solve those kind of combinatorial problem with very simple network component like this. The encoder decoder, actually the network architecture itself is not very complex, but when combine them together, it gets very good result for solving such kind of combinatorial problems.
I see. So the sequence can handle such kind of complicated combinatorial problem.
Yes.
Okay. So I take the question from Min Hyun Sung. So thank you very much for great talk. So he is asking that instead of reinforcement learning, for the upright orientation, estimation, instead of reinforcement learning, can you use a simple regression network for the upright orientation explanation?
Yeah. This is the basenet. I think what he or she mentioned is this kind of basenet. So because for each point cloud, we do know the ground truth upright direction, and we can use supervised learning method to do the regression directly. And from the experiment, as I show here, we found that use reinforcement learning can always get better result. I think especially for those partial data set and single scans. I think one possibility is that the shape have too many variations, especially when there are large missing parts. Then the simple supervised regression cannot really handle all those weird cases. But for reinforcement learning, it rotates the shape step by step, and somehow it finds a way to the better solution of the upright direction.
Actually, he means that iterates the regression progress multiple time in one step.
I see. Okay, I see. Okay, then the question the problem will be during the testing. You don't know how to stop, when to stop for the supervised method. For the reinforcement learning, we add the stop actions. We added the stop action, so we can know once we sample the stop action, I will just stop. This is the final upright direction we got. But for the supervised method, during the testing, you don't know when to stop. Sometimes, for example, you might already get a good result, but then you apply the supervised network again, it will derive away to the ground truth direction. I think it would be the problem.
I see. Thank you. Yeah. Is there another question from the
may I
audience?
ask?
Yes, please. Takeo, go ahead.
Yeah, so I found your grass transfer is very interesting, and I want to know a little bit more. So you predict upright orientation, right? And in the reward function, it's in the training, ground truth is given?
Yeah, during the training, we used the ground truth.
Oh, I see. Okay.
Yeah.
And then another question is, yeah, I'm impressed by the result. You know, your reinforcement learning result is much better than BaseNet, right? Directly feeding data. And my question is, when does this happen to many other questions? You know, replacing just simple network with reinforcement learning is always beneficial, or when reinforcement learning is better and when is direct regulation is better? Do you have any suggestion in general?
Yeah, I think from my experience, I think maybe there's one slide here in the beginning. Yeah, I think for those problems, if you have very clear goal, you know what's bad, what's better, what's worse, but you do not find a good way to construct the optimal solutions, or there are cases that there are multiple optimal solutions. So for the supervised learning, you have to choose one, right? You have to set the mapping from one input to one output. But when you have multiple optimal solutions, which one do you select? That would be a question. But when you know the way how to evaluate, how to measure whether a solution is a good or not, then you can use reinforcement learning to train a policy to find maybe the shortest path to any good solution. I think this is yeah, what I can see from my experience. When you have multiple solutions, or when you cannot really construct a set of good solutions, then maybe you using reinforcement learning with a good reinforcement, good reward function to guide the training will get better results.
Yeah, so thank you very much. But upright orientation, I think, is single ground truth, right? Not multiple.
Yeah.
So I'm confused.
That one, it has a single, how to say that? It has a single ground truth upright direction, but when you rotate the given input to the final position, the procedure is not unique. Like you can rotate the shape around the upright direction in multiple with any kind of rotations. You can rotate around the upright direction, so the whole process grasp and place the object, it's not unique. So in this way, yeah. So in this way, it kind of, using the reinforcement learning to find a path to that.
Yeah, thank you. I will try reinforcement learning more in the future. Thank you.
I have one quick question. So yeah, it's impressive that you use reinforcement learning for learning policy for the first project you presented for the packing. I'm curious how much it's generalized, for example, into different problem setting. For example, if the box size is different, then the network try to apply the same policy, but how much it's generalized, how much it performs good. For example, the container is different, for example, or box is different.
That's a very good question. Actually, in our paper, we test all those kind of different settings. I think the box size is not a big issue, because when you see the box I show here, like you have very tiny box here and very big box here. So the box size won't be a big issue, and since it's a static encoding in our input, but the number of boxes become an issue, because for the input, for the network, for most of those networks, it takes a fixed size of input. So initially, we always assume like we have 10 boxes, we have 20 boxes. And once we change the network for 10 boxes, it can only used for 10 boxes. But I think this makes the network cannot generalize well. So we have two ways to improve the, make it more general. Let me find the slides here. So one way is what we call a rolling scheme here. So when we have a larger instance, here, when we have larger instance, we, for example, here the network is trained on 4 boxes, but test on 6 boxes. So because we have encode the access constraints into the precedence graph, so we can always know which box is invalid currently. So in this case, we can choose the 4 most likely 4 boxes most likely to transpose and pack to give it to the network first, and then we pack the object. Once this object is removed, we can add one more object into our network, and then this the process iterates until all the boxes are packed. So this is one way how to deal with the larger instance with more numbers of objects than the ones we train. And another way is to modify our encoder. So previously, our encoder is a CNN network, CNN. So it takes a fixed number of input, fixed size of input. But later, we also tried here, if you can see here, these are convolution. So these are CNN. The input size is fixed. Later, we changed this CNN, use recurrent neural network. So once we use recurrent neural network, the input size can change. So then it can take more different size of the input. But once we after we do all those experiments, the difference cannot be too much. Like if our network is trained on like input with 10 boxes, we can deal with maybe 20 boxes, but it may not generalize well to 100 boxes.
I see.
So I think it has some degree of generality. Yeah.
I see. Yeah. Thank you very much. So we have reached today's time limit. So we have to conclude this session. Thank you very much for excellent talk for both Takeo Igarashi and Ruizhen Fu. We'd like to thank the speaker. Yeah. Thank you very much.
Bye.
Thank you.
for the
Bye.
organizers. Thank you. Bye.
Bye.
Thank you.
Okay.